In this video, the second video for section 3.3, determinants and inverses, we're going to look at two places where the theorem that you learned in the last section, which gave us a formula for the inverse of a matrix if the determinant wasn't zero. We're going to look at two theorems where that is useful. And the first one you can already see here. And this one is extremely important, perhaps even more important than the theorem that we used to prove this one. And it says that a square matrix is invertible if and only if its determinant is non-zero. So if you compute a determinant of the matrix and you get some non-zero number, that means the matrix is invertible. And if you compute the determinant and you get 0, then the matrix is not invertible. And remember, this invertible matrix idea relates back to linear transformations, because a linear transformation is invertible when you can find the inverse of the matrix for the linear transformation. So here's how you prove the theorem. And this theorem has two parts, so our proof will have two parts. First, we'll suppose that A is an invertible matrix. Then we can do a little bit of work. Then 1 is equal to the determinant of the identity matrix. There's nothing new here. But the identity matrix is equal to A inverse times A. And we know that A is invertible. That's why we're able to write down A inverse. And then one of the properties of determinants says that to compute the determinant of a product, we can break it into the product of the determinants. So overall here we see that 1 is equal to the determinant of A inverse times the determinant of A. But since when we multiply these two numbers together, the two determinants together, we get 1, that means that neither of these can be 0. So that means that A inverse, the determinant of A inverse, is not 0. So this is the first half of the theorem. If you assume that you have an invertible matrix, then its determinant is non-zero. Now we have to do the other half. We have to suppose that the determinant of a matrix is non-zero and then prove that it's actually an invertible matrix. But this is what the theorem that we learned last time does for us. It gave us a formula for the inverse of a matrix, assuming the matrix is square and its determinant is non-zero. So we actually don't have to do any work for this half. Okay. So that's the proof. And this theorem gives you an easy way, or relatively easy way, to check if a matrix is invertible without actually going through the whole process of computing the inverse. All you have to do is find the determinant and see if the determinant is 0 or non-zero. Here's another theorem. And this one has to do with systems of equations. So here we're going to look at an equation. Let Ax equals B be the matrix form of a system of n linear equations and n variables. So what this means is that A is an n by n matrix, X is a vector with n entries, and this is n unknown entries, and B is a vector with n entries again, but these will be numbers in B. And here's what the theorem tells us about this equation. If the determinant of A is not 0, then there's a unique solution to the system of equations. And if the determinant is equal to 0, then there are many solutions or there are no solutions. I didn't write out a formal proof of this one, but we can discuss quickly how this works. If the determinant of A is not 0, that means A has an inverse matrix. So we could go up to this equation, Ax equals B, and multiply on the left, on both sides, by A inverse. So what this does for us is cancel off the A and then we get x is equal to A inverse times B. So it actually gives us a formula using the inverse for the solution. And if the determinant of A is not 0, that means A is not invertible, and there actually isn't any way to just cancel off A. So that's why there are many solutions, or possibly no solutions. Let's do a quick example of how you might use this theorem. I want to determine if this system of equations has a unique solution. And before we try the theorem, we have to make sure that the conditions are satisfied. So we have to make sure we're looking at a system of n linear equations in n variables. And here we have two linear equations in two variables. So that does check out. And then what we have to do is make a matrix out of the coefficients, the coefficient matrix, and then find its determinant. So our matrix is 3, 4, 1, minus 2, as I've written. And then to compute the determinant, you do 3 times minus 2, minus 1 times 4, and you get minus 10. And minus 10 is not 0, so we go up to the theorem and see which part applies. If the determinant is not 0, then there's a unique solution. So that's our conclusion in the example. For this system of equations, there is a unique solution. So something to notice here in the example is that in order to answer the question, is there a unique solution to the system, we didn't actually have to do any row reduction or any solving or anything like that. And actually, it didn't even matter what appeared over here. It didn't matter if you had 11, 14, or 0, 0, like a homogeneous system, or anything else. All that matters to determine if there's a unique solution is the coefficients, or the matrix of coefficients that you make out of this here.